modern buildings consume enormous amounts of energy just to stay cool. Yet long before electricity existed, ancient builders developed surprisingly effective ways to beat the heat. Some of these techniques are so efficient that architects are still using them today to cut cooling loads completely. Welcome back to Next Gen Home Builders channel. Today we're looking at ancient cooling tricks that worked without electricity. Our modern residential architecture relies dangerously on active, mechanical HVAC compressors. We build glass-heavy minimalist structures supported by structural steel framing. But these design choices trap radiant heat like a greenhouse. This causes indoor temperatures to skyrocket, forcing cooling grids to run continuously. As urban centers grow, this concentrated heat rejection creates massive urban heat islands, driving energy costs out of control. But thousands of years ago, builders faced the exact same extreme desert heat without a single electric air conditioner. They couldn't rely on fossil fuels, so they had to out-engineer the climate using fluid dynamics and thermodynamics. But capturing wind was only part of the solution. To see this fluid dynamics mastery in action, we have to look at ancient Persia and their revolutionary architectural feature, the badger, or wind catcher. These are tall, hollow masonry towers built prominently above the roofs of desert homes. Mechanically, they operate on pressure differentials and the Venturi effect. The top of the tower features open ports oriented toward the prevailing high-altitude winds. As the wind hits the tower, it creates a localized high-pressure zone, forcing the cooler, fast-moving air down into the vertical shaft. As this air descends, it flushes out the hot, stagnant air inside the living spaces below, forcing it up and out of leeward exhaust vents. But the engineering gets even better. If there is no ambient wind, the tower works in reverse. The intense solar heat bakes the masonry brick at the top of the tower, heating the air inside the shaft. Because hot air is less dense, it rises and escapes out the top, creating a continuous vacuum that draws cool air up from the subterranean levels of the home. This entirely passive system can reduce internal ambient temperatures by as much as 10 degrees Celsius without a single moving mechanical part. But capturing wind was only part of the solution. In the ancient deserts of Egypt, Rome, and the Middle East, builders relied heavily on the physics of thermal mass. Modern homes use lightweight lumber framing studs insulated with fiberglass bats, which offer minimal resistance to extreme exterior heat waves over a long day. Ancient engineers built walls out of thick, dense materials like adobe mud brick, heavy limestone, and organic volcanic mortar, often measuring up to 3 feet thick. The core engineering lesson here is that ancient builders didn't try to permanently stop heat transfer, they intentionally delayed it. This is a thermodynamic property known as thermal lag. The dense adobe walls absorb the intense solar radiation slowly throughout the scorching day, preventing the heat from penetrating into the interior living spaces. It took up to 12 hours for that thermal wave to travel through the mass. By the time the heat finally reached the interior skin, the sun had set, the desert air had dropped to freezing temperatures, and the wall naturally released its stored warmth to heat the home overnight. Ancient builders also discovered that water could cool entire spaces. Another key macro design strategy used across ancient Rome, Islamic architecture, and classical India was the central courtyard. Traditional modern layouts feature outward-facing structures exposed to hot winds. Ancient homes were oriented entirely inward. A central, open-air courtyard creates an isolated microclimate inside the core of the building. Because the surrounding rooms cast deep structural shadows over the courtyard floor for most of the day, a pocket of dense, cool air is trapped at the ground level. As the hot desert wind blows over the top of the building envelope, it creates a low-pressure zone that gently pulls the stagnant air out of the surrounding rooms, causing the cool air from the shaded courtyard to naturally circulate through the open arches. This creates a continuous, passive convective loop that keeps the core living spaces comfortable. Ancient builders also discovered that water could cool entire spaces. To supercharge these courtyard microclimates, ancient engineers integrated water systems to utilize the laws of latent heat of vaporization, or evaporative cooling. In Persian and Indian palaces, builders constructed central stone water pools, flowing fountains, and shallow marble channels directly in the path of the incoming air currents. When hot, dry air passes over an open water surface, the water absorbs thermal energy from the air to shift its physical phase from liquid to vapor. This phase change extracts sensible heat directly from the airstream, instantly dropping the dry bulb temperature of the air while increasing its relative humidity. By integrating these water elements directly at the base of their wind catcher shafts, the incoming air was filtered, humidified, and chilled simultaneously, functioning exactly like a modern mechanical swamp cooler but with zero electrical input. But the most surprising technique may be the one modern architects are bringing back. The absolute peak of ancient thermodynamic engineering was achieved by utilizing the stable thermal mass of the Earth itself. Deep underground, soil temperatures remain completely constant year-round, completely isolated from ambient air spikes. Persian engineers built deep subterranean living chambers and connected them directly to qanats, which were massive underground aqueducts carrying mountain snowmelt. Air was drawn down into these deep earth shelters, passed directly over the ice-cold running water of the aqueduct, and was then channeled straight up into the residential rooms above. This combined the physics of geothermal cooling, evaporative cooling, and structural mass into one single uncompromised layout, keeping interior spaces comfortable even when surface temperatures soared past 45 degrees Celsius. But the most surprising technique may be the one modern architects are bringing back. Today, as global energy costs rise and the construction sector pushes towards sustainable, net-zero carbon footprints, modern structural engineers are actively bringing these ancient passive cooling concepts back to life. We are seeing contemporary high-rise commercial structures built with modern wind towers that utilize computerized dampers to route high-altitude airflow down through central concrete utility cores. We are designing high-performance passive houses that combine modern thick concrete slab thermal mass with automated shading louvers to mimic the thermal lag of ancient adobe walls. Contemporary desert architecture is proving that we do not need to rely solely on massive, noisy mechanical HVAC compressors if we design the physical bones of the building correctly from the start. Ancient builders didn't have electricity, but they understood something many modern builders completely ignore. The most efficient cooling system is the one that works with nature instead of fighting it. Thousands of years later, architects are rediscovering that lesson. Because at the end of the day, real engineering luxury isn't about how much power you can consume. It's about how beautifully you can manipulate the natural laws of physics. If you respect the power of uncompromised building science, hit that like button to help us grow. Subscribe to the Next Gen Home Builders channel and turn on notifications so you don't miss our upcoming structural breakdowns. Let me know in the comments. Would you build a modern wind tower on your next home? Thanks for watching, keep your tolerances tight, and I'll see you in the next analysis.